We're in section 2.3. Before we look at section 2.3, there's a note from the Disability Services. They're looking for a note taker in this class. So if you're interested in being a note taker, you should be someone who comes to class regularly or watches class on video regularly. It pays $60 for the semester. And there's 2 steps if you're interested in being a note taker. You will go to www.uwdb.edu/DS and you sign up as a note taker. And then not only do you have to sign up, then you have to request a note-taking assignment. So that would be when you pick this class. So if that's something you think you'd be good at, then you go ahead and sign up for that. It could be for this section or the other section. They're both, I've run all the sections the same. Does anybody have any questions on Wiley Plus? Or any other questions before we continue on in looking at prime cuts of numbers, section 2.3? Yes?
Yeah, so are we going to go over the proof again?
We are. That's how we'll start. Okay. Any other questions? Okay. So we're going to prove that there are infinitely many primes. We went a little fast last time. This time we'll talk about each step and make sure you can understand why each step is representing impeccable reasoning that's unassailable. So first we let M be any natural number we let M be any natural number. We need a prime larger than M. So that's our first assertion, that we need a prime larger than M, and that if we have a prime larger than M, somehow that's going to prove that there are infinitely many primes. So how would having a prime larger than M, where M is any natural number, how would that prove that there are infinitely many primes? Instead of just, say, 2,000 primes or 3,000 primes. How would having a prime larger than any particular number M show there's infinitely many primes? Yes?
Because if there has to be a number larger than M, then you have to keep going, so if there's always a number larger than any natural number.
Good, because then there's always one more.
Yeah.
Yeah, so there's always, you get to the 1 and then you're like, yeah, but then there's one more at least. So, okay, good. So there's always one more, so there's infinitely many. Okay, now we're gonna set up B. Let B equal, remember we use B for big, this is our big number. Let B equal 2 times 3 times 4 times ... times M plus 1. So we create B, 2 times 3 times 4 times ... times M plus 1. And now is another assertion. We're saying B is bigger than M. So I'm saying B is bigger than M. Why does that have to be true? Yes?
With M times the Well, plus m plus 1, but m times the other, whatever, natural numbers. So it's m plus something else, so b has to be bigger than m, because m is only up by itself.
Good. Because at the very least there's that plus 1, say if m was only the number 2, then you're adding 1 to it, so b is bigger than 2 plus 1. But if m is bigger than 2, why then it's also multiplying, at least times 2, before you add 1 on. Okay, good. So we got that assertion unassailable. So here's another assertion. B is either prime or B is not prime. So I'm saying these are the two options for B. B is prime or B is not prime. Why is that true? Or is it not true? Yes.
It's going to be true because there's only two options. So if it's not prime, then it has to be prime.
Good, because there's only two options. All the natural numbers are either prime or not prime. So those are the only two options. Okay, so if B is prime, we are done. Okay, so if B is prime, we're done. We found B a bigger number than M. That's prime. Okay. If B is not prime, if B is not prime, it has a prime factorization. If B is not prime, it has a prime factorization. So that was the prime factorization theorem that said every number is either prime or has a prime factorization. Because, that's the definition of not prime. You can factor it. In fact, you can factor it to a prime factorization. Okay, so that's what we're looking at. If P is not prime, it has a prime factorization. Then we'll let P be a prime factor of B. So let P be a prime factor of B. So we have this big number. If it's not prime, then P is going to be one of the prime factors of B. Okay. So if it's not prime and it has a prime factorization, P is one of those factors in there. Here's another assertion. P is not 2, 3, 4, ... M because 2, 3, 4, ... M don't divide evenly into B. So there's another assertion. Does anybody know what the remainder is if you divide 2, 3, 4, ... M into B? What would the remainder be? Anyone remember? Let's look back at when we actually made some B's up. So we made some big numbers up for examples. Let me find those in our notes here. Here we go. So earlier we planned a strategy on Monday, and we came up with these numbers: 2 times 3 times 1, that was B, when M would be 3 then. And here we had 2 times 3 times 4 plus 1, so the M would be 4, and the B would be 25. And then here we had M was 5, and so the B was the 121. So in these three cases, we had B come up to be prime once, so 7 was prime. but then we had 25 and 121 for B, the big number that we made, that was not prime. So go ahead and this left half of the room, please go ahead and see what the remainder is when you divide 25 by 2, 3, or 4. And the right half of the room, you have a bigger job, but you can do it. See what the remainder is when you divide 121 by 2, 3, 4, or 5. Okay, and online students, you pick one of those. You can use your calculator. So you're looking for the remainder, okay? So I'll just do it with 2. So if you take 25 and divide by 2, you get 12.5. So ignore the 0.5. Ignore the 0.5 and say 12 times 2 is 24. So that means that there's 1 left. 25 divided by 2 is 12, remainder 1. Okay. And then down here with the 121 divided by 2 is 60.5. So ignore the 0.5. 60 times 2 is 120. So there's 1 left. If you take 121 divided by 2, it's 60, remainder 1, because 120 from 121 is 1. Okay. All right. So did you try a few more? What was your remainder for the 25 divided by 2, 3, or 4? Anybody on this side? Well, you can tell me, what was the remainder for everybody? Always. We saw the 2 examples. It's 1. That's why we constructed the big number the way we did, because when you divide by any of these smaller numbers, 2, 3 through 4, you get 1 less than 25. So like 6 times 4 is 25. 6 times 4 is 24. So 25 divided by 4 is 6, remainder 1. Down here, 120 divided by 4, that would be 30, remainder 1, because 30 times 4 is 120. So the reason we construct the big number the way we do is because this big number does not divide evenly by any number up through the number m. It will always have that remainder 1. And that's why we can say in the proof, this prime, the prime factor of the big number b, is not 2, 3, 4, or anything up to m, because 2, 3, 4 through m don't divide evenly into b. You notice, then we can claim our conclusion. So p is a prime larger than m. So we found a prime larger than m. Okay, and in the specific cases we looked at on Monday, your prime larger than m was 5 in this case. So the 5 was larger than the 4. And in this other case, your prime was 11. Your 11 was larger than 5. You might conjecture that these are always going to come out to be perfect squares or else prime, and that's not the case. You can try some more experiments and see that. So our proof is beautiful. It's actually Euclid's proof. Euclid from Euclid's Geometry, not Euclid. So who knows how many different proofs he tried before he came up with this one. This is a beautiful, elegant proof. Each step is kind of simple in itself. The real genius of the proof is constructing this number right here, this big number that's not going to be divisible evenly by any numbers 2 through 4. That's the highlight of the proof. Does anybody have any questions? So this is a proof that I would expect you to be able to prove on a quiz. I would ask you to prove that there is no largest prime, or that there are infinitely many primes. So it might be phrased, there is no largest prime. And if you understand a proof, then it's easier to remember. But you will have your 3x5 card that you can put what notes on that you think you need. Did that clarify any, or do you still have questions? Anybody? Okay. Well, let's look at some other proofs. We'll look at Fermat's last theorem. How many of you have heard of Fermat's last theorem? Anybody? When I was in high school, Fermat's last theorem was unproven. And it seems like it should be such a simple theorem that it's been wrestled with mathematicians for more than 300 years. So this is the mostly true story of Fermat's last theorem. It was a dark and stormy night. Rain pelted the wavy window pane. Wind seeped in through, I gotta make this larger, I can't see. I'm trying out new contacts with my eye doctor. There's limited success so far. We'll see. A wind seeped in through cracks in the window frame. A candle flickered uncertainly in the cold breeze. The year was 1637. Pierre de Fermat sat in the great chair of his library, poring over the leather-bound Latin translation of the ancient tome of Diophantus Arithmetica. He concentrated intensely on the ideas that Diophantus had written 2,000 years before. During those 2 millennia, whole civilizations had risen and fallen, but the study of numbers bridged Fermat and Diophantus, spanning centuries and even transcending death itself. As the night wore on, inchoate ideas, at first jumbled and ill-defined, began to weave a pattern in Fermat's mind. He gasped as insight and understanding began to take shape. He was seeing how the parts fit together, how the numbers played on one another. Finally, it was clear to him. On that fateful night in 1637, he wrote in the margin of Diophantus Arithmetica the statement that would make him famous forever. He wrote in Latin, "It is impossible to write a cube as a sum of 2 cubes, a fourth power as a sum of 2 fourth powers, and in general any power beyond the second as a sum of 2 similar powers. For this I have discovered a truly wondrous proof, but the margin is too small to contain it." So this theorem was unproven, but struggled with for hundreds of years because his other theorems were proven. Fermat had a habit of writing down theorems and saying he knew the proof, but then not writing the proof down. I don't know why he thought that was fun, but it drove his colleagues crazy. Every one of his theorems, though, was proven except this one. And everybody thought, well, it must be true because he's a brilliant person and he said it. What would be the proof? Well, after hundreds of years, Andrew Wiles was able to prove this theorem. Now, his proof was not small and elegant. I don't think it was the proof that Fermat was thinking of, because he would not have said that it would fit it wouldn't fit in the margin. It would have taken way more than a book to fill it. In fact, Andrew Wiles' proof took 2 days just to present. So he worked on it for at least 10 years. And then he went to present it, and the mathematicians watching his presentation were spellbound, sitting on the edge of their seat to see if he had finally proven it. So the first day he went through so many areas of mathematics in his proof that only a few people sitting in the auditorium listening even understood what all he was talking about. But they went home and they studied on it, and then when he came back the next day and concluded his proof, they took all of that home and studied on it, and they all agreed, yes, Andrew Wiles did prove this. So let's go ahead and see what this proof is. Not the proof. We don't have the background for the proof. Let's look at the theorem. Like so many theorems in number theory, it seems very simple. Whenever you see the word theorem, that's something someone's proven. It stands on top of an impeccable line of reasoning and has stood up to people challenging it. Okay, Fermat's last theorem. So Fermat's last theorem says it's impossible that a cubed plus b cubed equals c cubed, a to the fourth plus b to the fourth equals c to the fourth, a to the fifth plus b to the fifth equals c to the fifth, dot, 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 for natural numbers a, b, and c. Okay. So Fermat's last theorem was saying that it is impossible to find three natural numbers where a cubed plus b cubed is c cubed, a to the fourth plus b to the fourth is c to the fourth, or so on. Okay, so the reason that this is so interesting, of course, is because of the contrasting theorem that all of you know. What's the one that looks similar to this that is possible? Yeah, good, the Pythagorean theorem. So there are lots of Pythagorean triples, we call them, numbers that make the Pythagorean theorem true. So for example, 3, 4, 5 make the Pythagorean theorem true because you'd have 3 squared plus 4 squared equals 5 squared. But for any other exponent besides 2, for exponent of 3, 4, 5, and so on, there are no triples like that. So Fermat's last theorem has been proven. Now we'll look at two open questions. So there's lots of open questions in mathematics. Those are questions that mathematicians have struggled with for decades or even hundreds of years. First we look at the twin prime question. So the twin prime question says, are there infinitely many pairs of prime numbers that differ from one another by 2? For example, 11 and 13, 29 and 31, 41 and 43. Those are examples of twin primes, primes that differ by 2. So nobody knows. Nobody knows if there are just a certain number of pairs of twin primes, like 2,392 pairs of twin primes, or are there an infinite number of twin primes? If you keep going and finding primes, are there more twin primes after that? So nobody knows, and nobody's been able to prove one way or the other. So that's one of the open questions. Here's another open question. The Goldbach question. The Goldbach question says, can every positive even number greater than 2 be written as the sum of 2 primes? Okay, so let's give you an example of that. In fact, this is your class activity. So you might as well write it down so you can take a picture of it. So the Goldbach question said, can every positive even number greater than 2 be written as the sum of 2 primes? So let me just pick a positive even number. Okay, so at your desk, how could you write 16 as the sum of 2 primes? Go ahead and do that, please. 2 primes. So don't pick 9 and 7. 9 is not prime. What is one way to do that? Anybody? Yes?
5 and 11.
Good. Anybody have a different way? I can think of at least one other way. Anybody think of another way?
13 and 3.
Yeah, 13 and 3. Okay. Here's another example. At your desk, write 24 as the sum of 2 primes. Anybody want to tell what they had? Yes.
I just started with around 19 and 5.
19 and 5? Okay, good. Anybody else? Yes.
11 and 13.
11 and 13. Good. So the go back question is, can every positive even number greater than 2 be written as the sum of 2 primes? So that's another open question. Nobody's proven that it's true that all the even numbers can be written as the sum of 2 primes, or that it's impossible. So you might think, well, couldn't you just send a computer going along with every even number? You know, the computer could go through and find 16, find 2 primes, add it up, oh, check that off, go to 18, find 2 primes, add it up, check that off. And you could have a computer doing that, but that's not a valid proof. It only goes as high as the computer goes. The computer doesn't have infinite time, so we don't have that proven. Yes?
Wouldn't it just make sense because all primes are odd numbers that they would add up to an even number?
That's true. All the primes, if you add 2 primes, they're always going to add to even. Very good. Yep. However, is there an even that's missed in there somewhere is the question. So we're adding up 2 primes, but is it going to miss one of the even numbers at some point? Any other ideas? Okay, well, we're going to leave the number theory there. If you're interested in number theory, though, there's lots of work that you can do there that doesn't take a great deal of background. So I think that number theory is kind of fun. Let's go ahead and take a look at section 2.4 then. The author starts section 2.4. It's called Crazy Clocks and Checking Out Bars. The author starts this section out with a question. Today is February 13th, January 2019. What day of the week will the 4th of July fall this year? So I'm going to ask you to work on, do not look on your phones. Don't look on your phones or Google, okay? Okay, then don't share. So I'd like you to use math to do this, but I found out in the last class that, at least in that class, nobody had learned a poem to memorize what months have 30 days and what have 31. Did anybody?
I was told it was every other.
Yeah, I
besides
learned on my
February.
knuckles.
It's almost every other.
March, April, May, June, July.
Almost. If you put them right together, so you're getting 2 knuckles together
I
that
just go
way.
backwards then.
Then you go backwards?
I just use one hand and I just go January, February, March, April, May, June, July.
But August has 31 and July has 31. So if you
Yep,
use your
so then I
knuckles,
go
yeah.
back-
Oh, you count it twice.
Yeah, I just go back into that same.
Okay, that'll work. Who all learned the knuckle method? Okay, good. Anybody?
I have a different method.
What's your method?
30 days of September, April,
Yeah.
June, and November. Yeah.
Yeah, that's the one. Let's write that one down because that's my favorite. But if you learn the knuckle one, then certainly use that. Nobody in the first class knew that. Did anybody else learn that poem? Okay, so a couple people. 30 days have September, April, June, and November. All the rest have 31. Except for February. Well, you'll need to know that, and then I'd like you to work in groups of 2 to 4 to figure out the answer to the question without looking on a calendar anywhere, okay? Okay, so I'll see how you're doing here. February 13th. Oh, yeah, it's off the screen. Today's February 13th. Okay. Tomorrow's Valentine's Day.
Then add all the months plus page.
Why does it say February 13th and then it says January 13th?
Oh, that's funny. I was typing and tapping without paying attention. Thank you. Nobody said that in the first class either. Okay, February 13th. Is anybody in this? You think you have it? Pardon?
141.
So you should explain to the people next to what you're doing, okay? So, what day of the week? Yeah, you guys, did you get, well, where did the 141 come from?
Well, I think it's adding up to
You got that?
January.
Good,
That's what he did, was how many days, right?
good place to start.
I had an idea, but now I'm not exactly what day.
How about in the start row?
Last year.
That's how I know, it's like a Tuesday.
Tuesday last week? No, Wednesday last week. Yes,
Okay,
I'll do it.
I before you find anything for
I don't know. Okay, so why did you have a strategy to come to Tuesday, or what did you? Okay. All right, we'll find a strategy.
All right.
Find a strategy.
I feel like it's every day. It's a day of this.
On a day that doesn't lie.
No one really cares on what day it falls on.
Well, my birthday's the day before. So I feel like I have to
What Sunday? What day was divided? I divided one. Every year I was a different person.
Somebody must have come up with a number and stuff that. Okay, that one they did, so that's good too. All right, what is your group think?
I can't
Okay, so guess who's Monday? Okay, so we all guess. That's one strategy.
Which 13 days on your Wednesday? Tuesday or Thursday? It's all Wednesday.
Okay, so I see some groups adding up the days, so that's a good, certainly a good start. Okay, so I see groups adding up the days of the months, so that would certainly be a good start. So if it's the 13th, we have 15 more days of February. 31, 30. So we're not going to do all of July, just 4 days. And then you added those up, and what did you get? You got 141? Okay, so that's a very good start. And the alternate way then would be to count by weeks. But we're going to take this route because this is related to circular clocks that we're going to be looking at. Because now that you know how many days, what do you do next? Did anybody go on from there? Yeah, Yeah, you want to take out groups of 7, right? Yeah, because like today's Wednesday, and in 7 days we'll have completed a week, so we can take out groups of 7. And that is actually kind of what you're doing when you count by weeks. You're taking out groups of 7.
So only have one more day, so we can Thursday.
Perfect. And you have one more day. So today's Wednesday. One more day after you take out the groups of 7, and you're at Thursday. So today is February 13th. Wednesday. 141 days till July 4th, or 20 weeks and 1 day. So this is section 2.4, where we take a look at modular arithmetic, or clock arithmetic. So we're looking at weeks, which are a natural cycle, and now we're going to look at hours of the day on a clock. So let's go ahead and make a clock. Okay, so we'll make a clock, and we'll say that it's 10 o'clock. So suppose it's 10 o'clock. And we're going to ask the question, what time will it be in? And then we'll have a couple different ones here. How about 38 hours? So it's 10 o'clock. What time will it be in 38 hours? It's the same kind of question, isn't it? Only instead of days of the week, we're looking at hours on the clock.
So you would divide it by 12.
Mm-hmm. That's right. You want to group that in groups of 12, because there's 12 hours. So if you think of the 38 as 12 plus 12 plus 12 plus 2 more, yeah, it'd be 12 o'clock. 2 hours more, because for the 12, your clock just goes around back to the 10, but then we go 2 hours further. So A was 38 hours. Then do B at your desk. B is 22 hours. Anybody want to tell what they got? You can ask the person next to you first if it makes you feel more comfortable. Yeah? So go around the clock once, so you can discard those 12 hours and then go 10 hours more, and that brings you to 8. Yes, you're correct. Okay, we'll try a real big one then. How about 412 hours? You might want your calculator. That's a little harder, so we can do that one together. If you do the 412 hours divided by 12, you get 34. So that gives you like a starting point. So you have 34.3 repeating, so that lets you know, okay, I can get 34 sets of 12 out of this. What is 34 times 12? God, 408. So there's 408, and that means 4 hours more. So the 412 hours you can think of as 34 sets of 12 plus 4 more. So the 34 sets of 12, the dial is just spinning around, spinning around, spinning around, spinning around. But then when you go 4 more, that brings you to 2 o'clock. Good. Yeah. So your calculator can get you started with the whole part of your division number to see how many sets of 12 you can subtract away. So 34 sets of 12 brings you to 408, and then you need 4 more hours to get you to 412. This is called modular arithmetic, and it does happen in real life when we look at the cyclical nature of the world around us. So here's our clock. Now we're going to look at the clock with just 7 hours, and that will be similar to days of the week, actually. So let's make a clock with 7 hours. Okay, so on the 7-hour clock, it is 2 o'clock. And the question is, what time will it be in, and then we'll have A, B, and C. Maybe we'll leave a little space. So A is 7 hours, B is 12 hours, C is 211 hours. So don't shout the answer out, but I'll come around and see how you're doing, okay? I'm figuring this out. So see how this works for you.
looking more at this on Friday, so if you wanted to look off on it, so you can look at it. Did you do it? It's a 7-hour clock. Yep, it's 7 This one is so this is 7-hour clock. So come back to 7. Do that count after B also. Isn't that 21? I mean 3. That's ridiculous. Great.
So the first two aren't so much that you can't count it off. So if you count off 7 hours, you go 1, 2, 3, 4, 5, 6, 7, and that brings you back to 2 o'clock. 12 hours you can count off as well. So we already know 7 brings us back to 2, 8, 9, 10, 11, 12. So 7 o'clock. 211, that's pretty big. So we're trying to take out multiples of 7. If you take 211, divide by 7, you get 30 point something. So I'm interested in the 7 times the 30. That's 210 actually. So I can see that the 211 hours is the 7 times 30 plus 1 more hour. So that's the one that I'm interested in because I go around the clock 30 times, so that uses up 210 hours, and then I go 1 hour further. So 3 o'clock. So I go around 30 times, keep going to 2, but then 1 more hour past that 30 times. Well, we'll be looking at modular arithmetic further on Friday. This is as far as my first class got, and I always try to keep the classes together. So if you have any questions, see me after class. I'll see you on Friday.